So we are given an array of k linked lists, each sorted in ascending order. We should merge all the linked lists into one sorted linked list and return it. For example, if we have these 3 linked lists, this should be the output. The lists will look like this, and when we merge all together, we get this one, a list of size 8, which consists of all the nodes in our 3 lists sorted in ascending order. So my first question to you is, do you know a similar problem which you have solved in the past? Yes, we do. That problem is merge 2 sorted arrays. If you don't remember the solution, I highly encourage you to take a couple of minutes and think about this problem, or even watch the video tutorial and do the coding tutorial again, as we will use that solution here. So, we will first start with a simple case, where k equals 2. Let's say we have these 2 linked lists. How can we adapt the solution from the problem with arrays to this problem? Well, instead of using 2 indices, integer variables, to traverse the 2 arrays, we are now going to use 2 list node variables. And we already have them. They are list 0, which points at the head of the first list, and list 1, which points at the head of the second list. We will use the dummy node trick in order to easier create the first node in our answer list. So we will first create an empty list node and store it in a variable dummy. Also, we will use another list node variable, which will point to the last node that has been pushed in our answer. Let's call this variable tail and initialize it with dummy. As long as we haven't visited all the nodes in both linked lists, so as long as list 0 is not null or list 1 is not null, we have to see which one of these 2 nodes is the smallest and push it into the answer. We will use a variable for this, index, which is initially 0. So we basically suppose that list 0 is the smaller node. Then we should check if list 1 is actually the correct node to be pushed into the answer. So, if either list 0 is null, or list 1 is not null and its value is less than the value of list 0, then index becomes 1. This means that list 1 is actually the smaller node. Now we know the correct node, so we are going to create a new node of that specific value and link tail to this newly created node. Now that we have visited and pushed into the answer this node, we should increment list of index so it points to the next node in that specific list, either list 0 or list 1. And then, because we have pushed a new node into the answer, tail should be incremented. Now let's see how this algorithm works on this simple example. And we enter the while loop. List 0 or list 1 holds true. So we initialize index with 0. We suppose that list 0 is the correct node. And then we check for list 1. Is list 0 null? No, it's not. Or, is list 1 not null? Yes. And the value of list 1, which is 2, is it less than the value of list 0, which is 1? No, it's not. So we don't execute what's inside this if statement, and we move on. We create a new node of value 1. We increment list 0, and we increment tail. And we continue the while. Is either list 0 or list 1 not null? Yes, both of them are not null. We initialize index with 0. Is list 0 null? No, it's not. Or, is list 1 not null? Yes. And the value of list 1, which is 2, is it less than the value of list 0, which is 3? Yes, it is. So now we enter the if statement and index becomes 1. And indeed, list 1 is the smallest node between these two. So we create a new node of value 2 and link tail to it. Then we increment list 1 and then we increment tail. And we continue the while. This holds true. Index is initially 0. List 0 is not null. List 1 is not null, but the value of list 1, 6, is not less than the value of list 0, 3. So we don't execute the if statement and index stays 0. We create a new node of value 3, we increment list 0 and we increment tail. And we continue. I will not keep going through the code line by line, but you can imagine what happens here. List 0 is the smallest node, so we will create a new node of value 4. We will link it to tail, then we will increment list 0, and then we will increment tail, and this is what we get. And on the next step, because now list 0 is null, index will become 1. We will create a new node of value 6 and link tail to it. Then we will increment list 1, which now became null, and we will increment tail. And on the next step of the while loop, we see that both nodes are null, so the algorithm stops. Now, do we have the correct linked list? Yes, we do. Now the question is, what should we return? What is the head of this answer list? And the answer is dummy.next. We will return dummy.next when the while loop terminates. And this is how we solve the problem for k equals 2. Now what about k equals 3? Can we do something similar? Of course. We will use our three pointers, list 0, list 1 and list 2. I abbreviated them with L because I don't have much space here. And we will apply the same strategy. First create a dummy node and initialize tail with dummy. Then, for as long as we haven't visited all the nodes, so at least one of L0 or L1 or L2 is not null, we will find the smallest node, push it into the answer, and increment the corresponding pointer. Again, we start with index equals 0, so we suppose that L0 is the smallest node. Then we check for L1. If L0 is null, so this node actually doesn't exist. Or, if it exists, and also L1 exists, and the value of L1 is less than the value of L0, then index becomes 1. This means that L1 is the smaller node found so far. And then we check for L2. The smallest node found so far is L of index. So, if this node is null, or maybe it's not null, and also L2 is not null, and the value of L2 is less than the value of L index, then index becomes 2. This means that indeed L2 is the smallest node. And all we have to do next is create a new node of value list of index.val, link tail to it, then increment list of index and increment tail. After the while loop finishes execution, we have our answer list and its head is also dummy.next. So you can already feel that this strategy can be extended for any number of linked lists. What we are basically doing is that we are using each element of list to store the smallest node which hasn't been pushed into the answer yet from that specific list. And for as long as at least one of these elements is not null, we find the smallest node between these k nodes and we push it into our answer. So for the general case, we create a variable dummy, we initialize tail with dummy, then we will first find out what is the smallest node from the initial ones, L0, L1, ... Lk-1. And we will use a function for this. The function is called minNode and takes as argument the list and returns the index of the smallest node in list. If we reach to the end and it so happens that all the nodes in list are now null, then list of this return index will also be null. So we can write a while loop checking if list of index is not null. While this happens, we will do the usual. Create a node of that value, link tail to it, then increment list of index and then increment tail. Afterwards, we need to know the index of the new smallest node. So we will again call this function and store its return value into index. And when the while loop terminates, we will return dummy.next. Now let's take a look at the function minNode. It's basically the same strategy. We initialize a variable index with 0, supposing that list 0 is the smallest node. Then we iterate through each index from 1 to k-1. And we check if list of index is null, or maybe it's not null, and also list of I is not null, and the value of list of I is less than the value of list of index, then index becomes I. And when the for loop terminates, we return index. And as you can see, we iterate through all the k nodes in list, so the time complexity of each function call is big O of k. Now let's get back to the main function and analyze its time complexity. The big question is, how many steps does the while loop do? Well, at each step of the while loop, we find the minimum node, we push that node into answer, and then we move to the next node from its list. So each step of the while loop corresponds to a different node from our k-linked lists. And if we denote the total number of nodes in these linked lists by n, our while loop will perform n steps. And for each step of the while loop, all the operations are constant except the function call, which we know takes big O of k, so the final time complexity of our algorithm is big O of n times k. The extra space used, if we don't take into account the new list which we should create and return, is constant. Now the problem, of course, is the time complexity. This is not the optimal algorithm, and the real issue is that finding the minimum node takes big O of k. We can optimize this. Let's recap. At each step, we first find the minimum node using the function minNode. Then we replace that minimum node with the next node in that list. And we do this in constant time. Each function call takes big O of k time to execute, and we can optimize this to big O of log k. And think about it. Does this sound any familiar? You basically want to hold a collection of elements. You want to quickly find the minimum element. You want to remove it and insert another element instead. All of that in big O of log of k. Yes, it is the min heap. The solution is to have a min heap consisting of all the current nodes in each list compared by their values. And let's call this min heap min nodes. We will first initialize it with all the elements of list, so the head node for each of the k lists. Then we create the empty dummy node and initialize tail with it. And now, for as long as min nodes is not empty, we will extract the smallest node from the min heap, so we get its value and also remove it from the heap. Then we create a new node of that value and link tail to it. And then, instead of min node, we should use min node next. So if min node next is not null, we are going to push it into the heap. And afterwards, we increment tail. When the while loop terminates, we will return dummy next. Now let's see how this algorithm works for the problem example. Min nodes is initialized with the value from list, so the nodes 1, 1, and 2. Then we create the empty dummy node. While min nodes is not empty, and it's not, then we extract the minimum node, which can be any of these two nodes. Let's say it's the first one. We create a new node of value 1 and link tail to it. Then we check if min node next is not null, and it's not. And so we push that node into the min heap. And we increment tail. Now the nodes in the min heap are 4, 1, and 2. Obviously it's not empty, so we extract the minimum node, which is 1. We create a new node of value 1 and link tail to it. Then we check if min node next is not null, and it's not, so we push node 3 into the min heap. Finally, we increment tail and continue. Now the nodes in our min heap are 4, 3, and 2. Obviously it's not empty, so we extract the min node, which is 2. We create a new node of value 2 and link tail to it. Then we check if the next node is not null, and it's not, so we push node 6 into the min heap and we increment tail. Now the nodes in our heap are 4, 3, and 6. We extract the minimum node, which is 3. We create a new node of value 3 and link tail to it. We check if the next node is not null, and it's not, so we push node 4 into the min heap. And so on and so forth. You can figure out by yourself how this works. You can complete this input example on your paper. When the while loop terminates, we will obtain the correct list and we should return dummy next. Now let's analyze the time and space complexities of this new algorithm. First major thing that we do is that we take list and we heapify it. And as you know, this takes big O of the size of the list time, so big O of k. Then we have the while loop, which still performs n steps, where n is the number of total nodes in all the linked lists. And inside this while, we extract the min node, which takes big O of log k time, and we push a new node into the heap, which also takes big O of log k time. All the other operations in this algorithm are constant, so the final time complexity is big O of n log k. But the extra space complexity will be different than in the previous solution. Now we use a min heap, which stores at most k nodes at a time, so the extra space used is big O of k.